talking about why we get this range, this 36 to 38 ATP. So we know that we get 2 NADH from glycolysis, right? The problem is that the NADH can't move directly into the mitochondria to then be part of those membrane reactions. So what has to happen is the NADH has to hand off its electrons and protons to a shuttle. And basically this shuttle kind of looks like this. There's 2 different shuttle mechanisms. In some cells, the NADH will hand its electrons off to NAD. And so basically they're just kind of doing this handoff. So NADH in the cytosol would be oxidized back to NAD, while in the mitochondria, 2 NAD would be reduced to 2 NADH. That's one shuttle mechanism. This mechanism has no effect on the final outcome of ATP. In fact, this shuttle mechanism is where the 38 comes from. It's the second shuttle mechanism where the 36 comes from. So again, we have the 2 NADH from glycolysis. And in some cells, instead of handing them off to NAD, they hand the electrons off to FAD instead of NAD. So now in this case, FAD is reduced to FADH2. Now if we go back and look at our counts, with the NAD shuttle, we have 2 NAD from NADH from glycolysis, right? And this is per glucose. We have 8 NADH from the membrane matrix reactions. We have 2 FADH2s from the matrix reactions. And we have 2 ATP from the citric acid cycle, and we have 2 ATP from glycolysis. So we know that the 10 NADHs and the 2 FADH2, along with our 4 ATP, is equivalent to 38 ATP, right? Okay, if we look at the FAD shuttle, instead of getting 2 NADH from glycolysis, instead we have 2 FADH2s. We still get our 8 NADH from the membrane reactions and our matrix reactions, and our 2 FADH2s from the matrix reactions, 2 ATP and 2 ATP from glycolysis. So we get 4 ATP from these 2 FADH2s, 24 ATP from these, 4 ATP from these here, and when we add all this up, it should be 36. So that 2 ATP difference then with that FAD shuttle is due to the fact that we have 2 FADH2s instead of 2 NADH2s. These 2 NADH2s would be equivalent to 6 ATP, whereas these 2 FADH2s are equivalent only to 4 ATP, so we get a difference of minus 2. 2 less ATP with the FAD shuttle. So that's where that range comes from. So certain cells use the FAD shuttle, other cells use the NAD shuttle. So next time you see 36 to 38, this is what you need to think about. Now when we look at these numbers, 36 to 38 ATP, about how efficient are these processes to get us these numbers? What did I say about that?
40%
About 40% efficient. In other words, of all the energy contained within a single glucose molecule, 36 to 38 ATP is roughly 40% of the total energy potential. So we're losing 60% of that energy. Where does it go? What did I say? It's lost as heat. When you break chemical bonds, heat is generated. And that heat helps to maintain your body temperature. That's why when you exercise and you're using a lot of ATP to sustain muscle contraction, and you're producing ATP, you're breaking down the glucose, it generates a lot of heat. So what's your body's response then to that increase in heat? Sweating. It's one of the responses. You also have some vasodilation occurring, et cetera, et cetera. Any questions on the membrane reactions? The electron transport and then the oxidative phosphorylation.
According to these, it makes FAD to FADH just with the citric acid cycle. But how does that tie in with the shuttle mechanism you have?
The shuttle mechanism does not affect what happens down here. The shuttle mechanism only affects the NAD produced in glycolysis. Because the NAD, if it's the NAD or the FADH2 shuttle, it doesn't matter. All these then would still go into electron transport, would still go into those membrane reactions. So what you'd have would be this. So with the NAD shuttle, we'd have 10 here and 2 here. With the FAD shuttle, we'd have 8 here and 4 here. So 10 would give us 30, and then the 2 would give us 2, that's 32. And then we would get another 2 ATP from glycolysis, and then another 2 ATP. I'm missing.
The 2 would give us 4.
Yeah, sorry, thank you. So that would give us our 38. But with FAD now, we'd get 24 here, we'd get 8 here, plus our additional 4. That's 36. So it's just affecting the amount of protons that are pumped into the intermembrane space to maintain that gradient. Now obviously this is all theoretical. I mean, there's going to be, as long as there's a proton gradient and 2 protons come through, it's going to make ATP. But whether those 2 protons came from NADH or FADH, it doesn't matter. I mean, we're looking at theoretical yields.